Okay. So we are going to talk about sensor networks. I don't know. Is there anybody here who is from the sensor networks group? Levin, are you in the sensor network? No? Oh, okay. So anyway, we share with the sensor network WirelessHART. So today we'll talk about what is special about sensor networks. Did I? Oh. Function F7. Continue recording. Okay, back to. So we are going to talk about 5 things. What are their applications? Then 3 different standards. We have already talked about 15.4 before, but just one more time because it is relevant here. Then 6 low pan and WirelessHART. And then research issues. There are 4 or 5 research issues, so that is quite a bit of it, but we'll just, those are the 4 things. So sensor means anything that can sense like temperature or chemical, biological sensors or moisture sensors. It could even be a meter, electric meter and things like that. Okay. Anyway, so you can see the applications. Big applications in military where they put sensors to see if there are any activities or any weapons and all that. They could have some. Can you give me another? This one, is there another pointer there? Somebody took it out? The black one? Okay. Too bad. All right. This is what you have to do now. Go to my office, and in my bag, which I carry to home, in the front pocket, there is a big pouch. Okay, it has a lot of stuff in it. You can just see this. Distinguish it. Let's bring that whole pouch. Chuck's I took it, I know, because somebody needed a pointer today. So, but so anyway, this is just a 1 second pointer today. It just goes for a second. So you can see the applications which are forest. In the forest, they could put a fire sensor. Actually, there are, and they have. I have seen studies where they are monitoring movement of all the animals, following where the different animals, lions, and so on and so forth, go at different times of the day. And then, obviously, for the medical applications, where we want to monitor some vital signs, and then the doctors can monitor it remotely. So what is the difference from Ad-Hoc? So we talked about Ad-Hoc last time. The biggest difference is that these sensor networks are generally large scale. Normally when you say Ad-Hoc, it could be 2 computers, or it could be 5 or 10 computers. Here we are talking thousands. So it's big, large scale. Second thing is, unlike the phones and the computers which can be charged every day, these have batteries that are just one lifetime. The battery is died, the sensor is gone. So you put the sensor in the field and you can't even retrieve them, right? May not have global identifiers, and so you cannot rely on having 48-bit or 64-bit MAC addresses. And the queries may be data-centric rather than address-centric. So the thing is, the queries are slightly different. For example, which of the 1,000 places the temperature is more than 95 degrees? So the question relates to the data and not, tell me what is your temperature, what is your temperature, what is your temperature, what is your temperature, which is just by addressing. It could be in the routing is geographical, and so because of that question is different, people have done research work on how to route such answers. I mean, if you have a temperature 95 degrees, probably the next door person has same 95 degrees, and so there is a way to aggregate and route and fuse, combine the data, aggregate, and so on and so forth. So basically, there are papers on that stuff as well. However, we actually today will not talk about data aggregation and fusion and so on and so forth, because that's a whole specialized field. All right. So anyway, so we will talk more about the protocols, and in general, what is more common, which is basically in practice used. So first thing is that all the protocols use this standard. So I'm going to talk about two or three other protocols, but they are higher layers which use this physical layer. The physical layer is 802.15.4, which is the low rate wireless personal area network. This is the same physical layer which is used in Zigbee. It is used in WirelessHART and MyWi and any other protocols. So this is has become very common layer. And we had this slide actually, or a variation of this slide and the next slide in our lecture when we talked about personal area networks. So I'm just going to reproduce here because we need it today. So it can reach up to 10 meters at 250 kilobits. And there are lower speed versions such as 20, 40, 100 kilobit versions. And then it runs in 3 different bands. In Europe, there is 868 megahertz band. In North America, there is 900 megahertz band. And worldwide, we have 2.4 gigahertz band. And these North American bands, for example, 900 and 2.4, are the familiar ISM bands. So if you know these telephones, when you buy a telephone, cordless telephone, generally they run at 900 megahertz and are 2.4 gigahertz, or then now 5.8 gigahertz. So those are the 3 common bands that those are ISM bands. Those are used for unlicensed operations. So that's same thing where we can use this those bands. And then 868 is a special band in Europe. So this particular standard uses direct sequence spread spectrum. Anybody remembers that standard? And that, what is that? Direct sequence spread spectrum, DSS. How does that work?
Isn't that where each bit is encoded in chips?
Right. So that is where you take one bit and encode it as 10 chips, or 100 chips, or 1,000 chips. So that is basically used here. And then it uses BPSK or QPSK modulation. So BPSK is basically binary phase shift keying. Binary means just you get 0 or 1, so 1 bit per hertz. QPSK takes 4 bits, basically 2 bits at a time, and makes 4 phase shift keying, quadrature for phase shift keying. So you get 2 bits per hertz. So anyway, so these are basically low bit rate standard. And we use these modulations to just save the battery that way, right? Now, after this 2006 came, then there are 2 other additions to it. 4A 2007 added ultra wideband, and another version of spread spectrum, chirp spread spectrum, and so I actually don't have the details on how does that work. So I will leave it at that right now. Then 4C and 4D, which added more phies and even more modulations. So anyway, this is one of the newer areas in wireless, and there is quite a bit of development and activity both in the industry and research in this area. Now 15.4 supports both star and what we call mesh topologies. In mesh topologies, you could go from one hop to the next hop to next hop, multiple hops. So here we say star and peer-to-peer and structured star. Now star is simply you have one center and lots of leaves, right? A peer-to-peer where you just talk to one and then they talk to somebody else, then they talk to somebody else, so that would be a mesh. And a structured star is more like a tree. So you have a root with many branches, and then each branch with many branches, then each branch with many branches, and so on. So, it is very general, and therefore there are two kinds of devices: full function and reduced function. Reduced functions don't do any routing; they just talk to the master, and whatever master answers, they answer that, and then the full function can do routing. Full function can act as a master, as well as they can forward it to other masters in the nearby area. So two modes, with beacon and without beacon. With beacon, the coordinator sends the beacon and the stop beacon, and so basically it says, okay, now time to start speaking and now time to stop speaking. The advantage of that is two. First of all, in the beacon there is some important information such as modulation frequency and the ID of this network and so on and so forth. And then also you can synchronize the time. So that is the beginning of time, beginning of hour, beginning of minute, whatever that is. Everybody has exact time. And then it could say that, okay, you speak and second slot, third slot, so all that slotting can be done perfectly, and that will not cause any problem. If there is no beacon, then there is no time, right? So then the problem is, then basically it is random access, and you speak at certain time, and then if you collide, then you back off. So that is also allowed. So that is very much like without beacon is actually, I mean, it's different than 11. I was going to say it's very much like 11, but it is different than 11, because in 11 we have both. We don't slot the time, but we have a beacon, and then we use random access. Yeah, that's the one. All right, we'll use this pointer. Huh? I know. Okay, so now let's just review 15.4 if there are any questions. First of all, 15.4 is for very low rate, for very short distance. Oh, actually one thing I wanted to say here for the beacon before. Okay, so let me say that when we come to that summary again. So very low rate, very short distance, and then it allows mesh networking. And that requires routing from here to there, long distances. So you really can cover longer distances, while the one phi layer will cover only 10 meters, but you could cover very, very long distances by going multi-hops. All right, is that clear? And then because of that, there are two kinds of devices. One which are normal ones, which just don't do all this multi-hopping stuff, and then the one which can do multi-hopping. Now, with beacon, there is one thing I wanted to point out is that there is a start beacon and there is a stop beacon, which is another new thing, because in 11 we didn't see stop beacon, or in any other protocol I haven't seen a stop beacon. So the start and stop really limits the time. So basically after a stop beacon everybody can go to sleep. So basically the network is not up all the time, right? So network might be running for some time, maybe every minute or every hour or every day, depending upon whatever it is. So there is a start and a stop. That's why they have a start and a stop. And to save batteries. All right, and then it allows both slotted stuff. Now with the slotted, the advantage with the slotted is that there is the efficiency goes up. When you have time synchronization, then the chances of collision are less, because then we know which slot is either assigned to me or we are going to try, as opposed to totally random access. Okay. So any question about any of these points? All right. Then we move on to the next layer up. So the first standard related to this is something called 6LoWPAN, which is actually an IETF working group, and it stands for IPv6 over lower power wireless. Personal area networks, lower power wireless personal area network. So basically the summary is IPv6 over IEEE 802.15.4. So IPv6 is obviously the third layer. There are some issues as to what is the problem with running IPv6 over this protocol, because the maximum size allowed on 802.15.4 is 127 byte, and the minimum size allowed on IPv6 is 1280 bytes. Right, so right there is a mismatch. Somehow when IPv6 people designed the IPv6, they said, well, we will just get rid of this whole business of MTU and negotiation. IPv4 does MTU negotiation, so you could have whatever size you want, but when the packet comes in, you can either, somebody can find out what is the MTU size, or the packet will be fragmented. So they said, we don't want to fragment anything. So they have fixed size, 1280 byte as the minimum transmission unit, right? So nobody will send anything less than that. Well, so that causes a problem. So out of 127 byte, 25 bytes are used up in framing, 21 bytes for security. That leaves only 81 bytes for the higher layer. You can just send 81 bytes into it, and it will go through 15.4 and show up on the other side. So basically what you need is you need something below IPv6, another layer, which is LoWPAN, 6LoWPAN. So what this layer does is it takes these big packets, converts them into little segments, sends them through 15.4, and then reassembles at the other end. Right? So that's what we need this new standard for. What it also does is it compresses the IPv6 headers. Now IPv6 headers are big, 128 byte address on a 127 byte packet is going to be a bit too much. So that's another thing, is that the headers are compressed and the addresses are compressed by actually using either 16-bit local IDs or 64-bit addresses. Okay, so basically this 6LoWPAN is a layer 2.5, which we can call an adoption layer that compresses the IPv6, which is layer 3, and allows PAN to be connected to regular IPv6 networks. So you could have an IPv6 on this side, IPv6 on the other side, LoWPAN in the middle. LoWPAN will let you go over 15.4. Clear? Okay. All right. The next standard is WirelessHART. So, has anybody heard of X1 devices that you use for in the homes? X1 control devices? Nobody has heard of that? X1? All right. If you want to do any remote control of devices in your home, suppose you want to turn on the light on the second floor from your first floor. You can do that by buying these adapters. You can go to a hardware store and they sell you these adapters that will allow you to remote control anything, anywhere in the house. All right. So similar to that, there is a standard called HART, H-A-R-T, and now there is a standard called WirelessHART. So what it does is you can do remote monitoring and control. Sitting here on your computer or on your controller, you could control a lot of devices. This picture shows cameras. So you could probably monitor the cameras, but it could be any other device. It could be a temperature sensor, it could be a light sensor, it could be any of the sensor things we are talking about. So WirelessHART, right? So basically what is HART? HART is Highway Addressable Remote Transducer, and I don't know how that name came about, where the highway came in from. But basically that is a old standard which is used in the current environment in industry. And the way this standard works is that normally you have a 4 to 20 milliampere analog loop. What that means is that when you have a thermometer or anything like that, a 4 to 20 milliampere, actually somewhere between those two, the current goes through that loop, and depending upon what the temperature is, the current could be 4 milliampere or 20 milliampere, or could be 15 milliampere, and that tells you what the temperature is, right? So there is this current loop. So when this was an analog loop, so designers of HART said, well, we can do better than that. We can use some very low level current, AC signal, very low level AC signal on the top of that direct current, right? So with this low level AC current will not affect the DC devices because it looks like a noise to them, right? Very low level noise, but we can send some digital signal through that, right? So they use frequency shift keying. Frequency shift keying could be very simple. You could have binary frequency shift keying where you use just like random number, 100 hertz for 0 and 200 hertz for 1, right? So whenever you get a pulse or a sinusoidal wave which is 100 hertz, they send a 0. If they send a 200 hertz, which is smaller pulse, then it is 1, right? So that is the phase shift keying. So that kind of signal is sent and received on the other side. So now we are doing both. On the original wiring, which was designed for analog communication, we are doing some digital communication also. Is that clear? What HART does? Now once we have that, then we have the whole digital protocol for rest of the layer. So we have a master and a slave protocol where we can now talk to the device more intelligently. It is not just measuring the temperature of the room. It could be just saying that please shut off or increase the temperature or decrease the temperature, or it is 10 o'clock, decrease the temperature at 11 o'clock. So there is a lot of remote control can be done. So a master-slave protocol is done, and there are two masters allowed, with one primary master and a secondary master. So that way, if primary goes away, secondary can take over. Then it allows both point-to-point configuration as well as point-to-multipoint. Point-to-multipoint means on one line there are multiple devices. Okay, so that is a multi-drop configuration, and there is a full 7-layer stack. So the HART was not only this FSK thing, but also 7 layers, and that brings us to the next slide, which is you have layer 1, 2, 3, 4, and 7. Basically, that similar to the IP protocol, we have physical layer, the media access layer, the routing layer, the end-to-end transport, and the application layer. Right? Full stack. For layer 1, they use frequency shift keying. Layer 2, they specify basically this. It's not just frequency shift keying. Actually, this is that 82.15.4. Well, hold on. Not yet. This is not wireless. We are talking about the wired protocol still, because this HART is wired protocol, and then there is a wireless version of it, which is WirelessHART, right? So we are talking about the old HART, which is the wireless wired protocol. So in that they use frequency shift keying. On layer 2, they have a master-slave protocol, and the master-slave, when you have multi-drop, basically we did not cover HDLC in 473, but if you cover HDLC, what you do is you say, okay, slave number 1, do you want to talk? Slave number 2, do you have anything to send? Slave number 3. So you poll. So this one can control up to 15 devices. Then there is routing at layer 3. There is also security at layer 3, so there is encryption and the key generation and all that. Then there is the end-to-end protocol, which, like TCP, but not really TCP. And then at the layer 7, there are some commands, some responses, some data types, and status. So there are some standard things that you can do with the device, and for that they have all these command responses. Now, not only standard things, but you could also do some very specific things. So there is something called device description. Now, I don't know how many people remember a MIB. What is a MIB? Anybody knows what is a MIB? Yeah? Management Information Base. So that is what is used in SNMP. What is SNMP? Simple Network Management Protocol. So when you want to manage a network, you have to have a protocol. SNMP is the protocol. But SNMP is very simple. It just has 4 commands. It says tell me, and here's the number, get, set, and things like that, right? But what you set depends upon the device. So what we do is we set up a MIB. We set up a what we call Management Information Base, which says for this device, for this computer, these are things you can set. You can set a screen resolution. You can set a screen brightness. You can set up a keyboard. So all that is put in the Management Information Base. But if somebody gave you a Management Information Base for a device, then you can talk to it in its own language. Right? Basically, you can say, well, do that variable number 3, change that to 5. So similarly here, they have a device description which specifies the functions and features of a device. And so for that, there is a description language. Just like for the MIB, there is a language. Here, there is a language to describe these things. And then you can compile this description so that machines can use it directly. So people prepare a MIB, and then the MIB is fed into some kind of program, and that program produces something that can be used with any monitor. Okay. So similarly here, this is actually a MIB. They don't call it a MIB. They call it device description. All right. So before I go further, by the way, all of these things are from these Wikipedia places. Okay, and those are the best places I find for you guys to go and refer. So make sure that you go and read these pages. Okay, one of the things that I'm missing is a textbook for this course, and so I have decided to put the pages where the information is so that you can go back and read more about it. So just don't have to depend upon the lecture alone, but so make sure that you read these, and I have put it on almost every slide. And if you download the PDF version of this slide from the website, then you can just click on those URLs. Okay, any question about this? All right, so this is a protocol designed in old days actually. HART has been around for quite some time, I don't know, 10, 20, 30 years. For remote device and control, but when the wireless became popular, then we need WirelessHART. Okay, so this is extension of HART to wireless, and so all they did was really to do extension is to start using 802.15.4, right? So that is the extension. Now the physical layer can be wireless, and it uses this radio is in 2.4 gigahertz, and it supports star and mesh topologies. It is self-organizing and self-healing. What is self-organizing and what is self-healing? Self-organizing means that the devices discover themselves. So you put a thermometer here, you put a camera there, and you put this, and they all speak HART. They will find out themselves. All right, you don't have to sit down and then program it. I mean, you probably have to program it before you put the devices anyway, because you'll have to tell them that you are part of this WASHU network and not the previous home that you were in. But after you have done that, they will discover each other, right? So self-organizing, self-healing. Can you guess what self-healing could be? What is healing?
Like if it loses a node, it routes.
Yeah.
It can automatically select another.
Right. Healing means if you get injured, you can heal yourself. And what is injury here is some node goes away. If something breaks, then it automatically reorganizes so that nobody has to do it manually anything. And remember, these are large number of devices, so really you don't want to have any manual intervention. So that's the main thing. All right. And 802.15.4 actually we said does DSR, sorry, it does the direct sequence. It also has a frequency hopping component. And so when we do frequency hopping, just like Bluetooth, when we do frequency hopping, some frequencies can be blacklisted. So you probably forgot all about Bluetooth, but if you go back to Bluetooth, it uses the whole 2.4 gigahertz, 73 megahertz at 1 megahertz interval. So it uses 73 frequencies, right? So in this case of 802.15.4, we can blacklist some frequencies. We can say don't use that channel 6 because Wi-Fi devices are using it. Okay, so you can do that. It uses 128-bit encryption, so you can securely read and control. It uses multi-path routing. So multi-path means to go to the same place, we have two paths. And so go from here to there. We try alternate paths, and we try both paths. In this case, they recommend that you try one message this way and one message that way, just to ensure that the second path is up. If the second message doesn't make it, then you know the second path is not up. If the first message doesn't make it, then you know the first path is not up. So this is that way. It also helps ensure that the paths are up and that you have good two choices. All right, those are the wireless HART extension. Again, these are the references. Now, if you have a device already from before, which most of the old industry complexes already have all these places where they want to monitor. Now, if they want to monitor wirelessly, then you can just buy an adapter. You can buy a wireless HART adapter, which you can attach to any device, and now that device can be controlled remotely. Right? You could buy gateways which connect you to backbone networks. So if you go back here, this is a gateway. Right? So this is your sensor network and this is your backbone network, this Ethernet. Right? So the gateway connects sensor network to the gateway network, the usual function of a router or a gateway. Then you actually, let's just go back and forth between this slide and the previous slide. I should probably put that picture here as well. But anyway, then there is a network manager that manages the routes. There is a security manager that manages the security. There are repeaters that simply extend the wireless range. So if you want to reach some device which is far away, let's say 20 meters, and your range is only 10 meters, then you can buy a repeater. So it will receive and then forward. Adapter, I think we started with the adapter here. Wireless HART adapter that attaches to the device that do not have the wireless HART. So all of these devices actually can be seen, some of these devices can be seen here. So what they are showing here is these are wired HART devices, and there is an adapter here. That adapter makes it wireless. Right? Then there is a network manager, there is a security manager. Now these don't have to be two different boxes, but these are two different functions. So the security manager worries about authentication and things like that, where the network manager simply worries about what is happening in the network, right? So all of these devices, device and function can be bought. That is what wireless HART is all about. Okay. Now, any question about wireless HART? All right. Then we just talk about some common terminology. I thought it would be good if you said that you took a course on, or you took a, not a course, actually there is a whole course on sensor network, by the way. But if you had a class on sensor networks and you didn't know what is a mode, that would be really bad. So I put this slide together which shows a sensor node. So when you have a sensor node, you generally have some sensors for sure, and these sensors are analog, so we have to have an A to D converter, which is analog to digital converter. So if the temperature is measured, then that is converted into digital format here. Then there is a computer, tiny computer, microcontroller that reads these converters, and then it has a memory and battery as usual, and then it has a transceiver which is wireless. Right? So this is where 15.4 resides. This is like a transmitter and a receiver. So this is a common configuration of a sensor node. And you can go to the companies and they are selling these devices with wireless and computer and sensor built in. All right. And one of the first companies was Dust Networks, which is actually a startup by a professor from Berkeley. And there was a DARPA funded project called Smart Dust. That's where the technology was developed. So and the name really indicates that it is very small size of a dust, right? I mean, right now it is not size of a dust; it's more like this size. But eventually it will become so small. All right. So they call those devices modes. So mode is not a standard name, but mode is the device name of these small sensors. Those are sold by the Dust Networks. Now it has become a very popular thing. So when you go and talk to sensor people, will say, I have 15 modes, I'm working on the modes, and so on and so forth. So the mode is a sensor node. Okay? And the operating system that runs on these modes is called TinyOS. So just like Linux, Windows XP, and Mac, we have another operating system called TinyOS. Okay, which is a public domain operating system designed for sensor networks. So I just wanted to introduce those terms so that when you talk to anybody who is working on sensors, you know that they're going to talk about modes and TinyOS and things like that. Okay, and obviously if you do research in sensor networks, then you will be taking multiple courses on sensor networks, including programming TinyOS, programming the modes. And so this is just a brief introduction to the sensor network area. So these are all the references. Okay? Any question about this? All right, that brings us to the research topics. So there are 5 research topics. Actually, I mean, these are not complete list. Actually, the sensor network again is a very active area over the last over the last 2003, about 7 to 8 years. Okay, 7 to 8 years ago, NSF decided, actually 2001. So 9 years ago, NSF decided that they want, just like they have right now Future Internet Architecture program, they decided that the key area that we'll be working on is the sensor networks. There will be a lot of funding. So lots of universities started working on that. And so there are lots of problems and books and so on and so forth which have appeared in that time. So I am just going to talk about 5 problems here and just give you a flavor of the type of the research that they are doing. Okay. So there is a problem of location discovery, and the next 5 slides are on these. So right now just let me list those problems and then explain each of them in the next few slides. Quality of sensor network, time synchronization, transport layer issues, and real-time communications. So first of all, location discovery. So when you have a sensor, the sensor has to find out where it is. So when it tells you that the temperature is 5 degrees or 95 degrees, you have to know where it is, right? So how does it find out where it is? So that there is a whole set of research on that. And so there are several ways. One way is indoor localization. So if you are inside and you know 3 other nodes which are your neighbors, if they know their location, you can figure out your location. How can you figure out your location? because you find out your distance. If I am distance x from this node, then I am in this circle, right? If I am at distance y from this node, then I am in this circle. So that means I am in this intersection here, right? If I am at distance g from this node, then I am in this circle, and that means I am in this area right there. Right? So by measuring the distance from 3 nodes, you can pinpoint your position in 2 dimensions. Right? If you just measure it from 2 nodes, you cannot pinpoint it, because then you are in this intersection. Right? But if you measure it from 3 nodes, then actually you can, it may be that there is a big intersection there. 3 circles can intersect in a big area, and then you won't be able to pinpoint it, but you know, you will be able to do in that area. Right? All right. So that is what it is basically, is that most of these things are exactly that, is that you find out reference nodes and you need to find the 3 references, and so there are all these papers, iterative multi-iteration, and then you keep doing it. Once you know your node location, other people can find you their location from here, and so on and so forth. So there is iterative and collaborative multi-iteration where people, they find their location and they find their location and they can find their location, so everybody knows their location. So this is what is location discovery is all about, is trying to find circles or spheres and then finding the intersection. In fact, the homework is about that. I mean, basically, we'll come to the homework in a minute. But anyway, so GPS works very similarly. Now, GPS is a common word today, and this used to be that we wrote our first GPS paper 95, 96, and at that time it was not very common. So GPS is global positioning system. That's exactly what it is that it tells you exactly where in the globe you are, in the world you are, right? Well, how does it do it? Basically, they have some satellites in the sky, and you measure your distances from those satellites. We know exact position of those satellites, and if you know your position from 3 satellites, you can put yourself in 2 dimensions. If you know from 4 satellites, you can put yourself in 3 dimensions. If you know from 5 satellites, you know, and so on and so forth. The more satellites you can see, more exactly you can figure out where you are. Right? So when you have it, many of you have GPS and have seen GPS. So it tells you that it's connected to 12 satellites, are acquiring satellites. So you're just trying to connect to the satellites. So US Department of Defense put 24 satellites in the sky. All right? And this was not for you and me. They wanted to use it for military purposes. So what they did was they put some randomness on these signals so that you could not figure out your exact location, or the enemy could not figure out their exact location using the satellite signals. Right? So this was in the original days. I think this has been removed. But in the original days, for the first 20, 30 years, GPS satellites have been around for a long time. But in the original days, the signal that you would receive had some random component to it. So your accuracy would be like, you know, within 30 or 40 meters or maybe 100 meters. But military could figure it out in 1 meter. Much more accurate. Commercial people could not. So the commercial development was hindered for that reason. And now it is actually, I think that it has been removed, and I'm not sure. I will have to figure that out. So now you can very accurately see your position even in the commercial devices, and that's why it is so popular now. Now within 30 meters you can figure out. So if you're on the highway, the GPS can tell you whether you're on the highway or on the next road. All right. So all you're doing is triangulation. What is triangulation? Trying to measure the distance from 3 different points. It could be quadriangulation too, but basically that's roughly the same thing. So the satellites broadcast the current time and their location using a direct sequence code. And we just a minute ago we talked about direct sequence. So this is that direct sequence code, and they use 1023 chips per bit. very high number of chips, right? 1023 chips per bit. That means that, I mean, basically it is very accurate signal in the sense that if you lose many of these things, you still get 0 or 1 correctly. All right. And it is actually this is a very low powered signal, but it's still, because of this spread spectrum, we can get it. If you get from 3 slides, you can figure out X, Y, and Z. If you get 4 slides, you can figure out X, Y, Z, and T. T is the time. So, and you can correct, if you get more slides, then you can correct for the delays experienced to the atmosphere. Now, when we measure the distance, we might assume that this is a direct line of sight, but the signal might not go direct line of sight. It could go like this, because the atmosphere is not homogeneous. Atmosphere may have different layers, and the waves may not travel a straight line. So, because of that, there might be delays through the atmosphere, and you could correct those by having these multiple satellites. All right? Okay. So, any question about GPS? So nobody has a question about how do you find 3 XYZ from 3 satellites? Basically, what you do is you draw a sphere, draw another sphere, right? Then you have this mass, which is intersection. Then you draw the third sphere. Now you have a zone, which is intersection of 3. So you have XYZ, but with some error, right?
So triangulation is the same as the multilateration?
Yeah, it's just triangulation, and you can say for 4 quadriangulation, and for 5 something else. So yeah, multilateration is just basically n ways, trying to find out your intersection of n spheres. Okay, so much about positioning. Now the question is, if you have a battlefield and either it is enemies or yours, if it is enemies, then you want to find a path which is least infected by bombs or mines, things like that, whatever you, right? And if it is yours, then you want to make sure that it is most infected, so the enemy cannot walk through without anything, right? So they have something called quality of a sensor network. It is measured by 2 things, exposure or coverage. Exposure is that exposure actually decreases with the distance from the target. So if this is your sensor or a target, and you are far away, your exposure decreases. Okay, and if you are very close to the target, then your exposure. This is like a bomb. If you are very close to the bomb, you are going to be killed, right? So you want to be as far away as possible. Now, if somebody gave you these locations of all these targets, then you want to find a path which is the safest path, right? So this is the safest path. Why the safest path? Because it is fastest that you can be from this target and from this target. Then this is farthest which can be from these 2 targets, and so on and so forth. All right, and so people have published papers on this kind of stuff, exposure, how to find the exposure, and coverage. Coverage is just the opposite problem. Coverage is how well the region covered with sensors. So we want to find the least covered path that could be followed by the enemy. So we'll just do the same thing and figure out what the enemy will do, and then maybe we need to put the target right there. Okay, and the technique is using what they call Voronoi diagram, where you basically you find the distance from the nearest sensor and find the maximum cost path, and so on and so forth. So again, I'm just going to give you a flavor of what they are doing, and if you need to ever work in this area, then you have to go and read as to how to do that Werner diagram exactly. All right, we are trying to find a path that has the maximum distance from specified points, and so you just there are ways to find that. All right. Third kind of problem that people have worked on is time synchronization. Time synchronization means we all have to say that it is 9 o'clock or 11 o'clock or 10 o'clock. How do we synchronize the clock? Well, if you had GPS, then that would be easy. GPS, you can measure the time, I can measure the time. And so most of the outdoor devices such as base stations and planes and things like that, they use GPS. That's the easiest way to get the time. Right? But if you don't, if you are inside a building, you can't get GPS because inside the building the signal doesn't come in. And so then you have to find somebody who has the time, and then you have to find the one-way delay from them. You have to find out how much far away from you are in time they are, and then so you have to find out what is the sending time, what is the access time, what is the propagation time, what is the receiving time, and maybe your time accuracy will be this order of this propagation one-way delay. If you are from me 3 seconds away, then I mean basically what I will do, I will take your clock and subtract 3 seconds, but it could be off by a few seconds because of this. All these times are not very well known. Best to timestamp the messages at the file layer of the receiver. Now the timestamp could be put at the application layer or the MAC layer or the routing layer, but obviously you want to put it at the bottom layer because that is when we know the packet is going to leave and not will be buffered. And then post facto synchronization. So people have now, again, these are the things that people have written paper on. In my first version of this talk about sensor networks, of this lecture of sensor networks, we used to talk only research problems, because that was the time in the beginning of 2000 we just had research problems. They were not real applications. But today these standards have come up, so I've divided into half and half. So here the research problem used to be is the post facto synchronization. When you announce the time along with the event, and everybody else synchronizes to that, and the leader periodically sends a sync message which goes to everybody, and then and the leader is elected using a random number. So we are 15 people, we all have our clock. So how do we do synchronize? Basically I send a random number and I say, well, my clock is so much and my number is 15. You send your clock and you say my number is 13. So whoever has the lowest number or highest number becomes the leader, and we all synchronize to that clock. Right? So it's important to have one clock and not so important to have that synchronize with the outside world. It might be just that we have to synchronize among ourselves. So we can just select a leader and then synchronize to that. Now what happens is that if there are two partitions, if suppose there is one partition that becomes two, then now you have two leaders and they have their own clocks. Now when they merge, now there is a problem. Right? So when you merge the partition, then one says it is 10 o'clock, and one says it is 9:59, then the summary is don't make it 9:59. The sum, when you have two clocks, just go forward. Otherwise there will be a problem, because some things that happened on my clock at 9:59 and a half, and on your clock they were basically 9:58 and a half. There will be confusion as to what is 9:59 and a half. So basically advanced. So this is a common thing that when you are doing file synchronization, for example, if you are doing file synchronization on two computers, and this always happens whenever there is this daylight shaving changes, that the times are all wrong on this computer and that computer, files are all different times. Then what do? You just go to the one which is ahead. Okay, that's the guideline. So much about time synchronization. Time synchronization means that we basically have to exchange the timing, and we have to estimate the delay, and then and that's how we can find the time. And the other thing is that basically in some cases, if it is just a group which is trying to agree on a clock, then we just randomly select a leader and we just all use their clock, or its clock. Okay. Transport layer issue. Transport layer issue is more like a multi-hop issue here when you are sending the issue, and again these are all actually sometimes just one or two papers on the area. So I mean I have started giving less emphasis to these things because I mean, it's not something that 100 people have worked on it. So there's this example, PSFQ. PSFQ stands for pump slowly and fetch quickly. So that is here, pump slowly and fetch quickly, PSFQ. So these people, they worked on the issue of how much should you transmit. I mean, how often should you transmit in an environment where you really want to minimize the battery and all that. So their rule is that there are two things we are doing here. We are getting it from the previous hop, so asking the previous hop to retransmit if error, that is called fetch. Fetching is getting the information from the previous hop. Forwarding is pumping. Pump is the forwarding to the next hop, right? So their rule is PSFQ, which is pump slowly and fetch quickly. That means if you really didn't get something right, make sure that you get it as soon as you can. Fetch quickly. And once you have something, then basically you send it off, right? So your sending has second priority to getting. Why? Because that way you will minimize the storage and maximize the reliability. Okay? PSFQ. And then basically in this particular scheme, the last node, the farthest node, sends a report of delivery status to the source. So this is like an end-to-end acknowledgement. You get the end-to-end acknowledgement. Intermediate nodes append their status to the same message. And so when the acknowledgement is coming back, in that the intermediate nodes send their status. So basically it is not for that message, it is for whatever else is happening in the network, that I have 3 packets waiting, our packet number 3 is with me. So all that status goes in the acknowledgement which is coming from the end. So one status message goes back, and you get the status of the path and the packets on the path. So this is just an example of a research on the transport layer issue. Another one is real-time communication. Before I go to real-time communication, any discussion on the transport issues? Any question? How? Yeah, how? Okay. So how does it adapt and minimizes the storage? Is that if you didn't fetch quickly, then you will be waiting for retransmission. You'll be waiting for retransmission. So let's say you didn't get packet number 2. Sorry, you didn't get packet number 2. Now you cannot send packet number 3. Right? So 3 is going to use the storage. Right? So you better get everything in order and send it, right? So rather than, so there are many things we can do at this time, but make sure that if something is missing, we get that first, right? By getting that first, everything is in order and everything is ready to be sent. Otherwise, some things will be waiting because they're waiting on something else which has not happened. Okay, so this is basically the idea is, and that's a good question, because I mean, otherwise it is not clear as to how by getting, but basically we're talking about retransmissions here. So retransmission means something was sent and something after that was sent and previous thing was not received. So out of order issues. Clear? All right. So the next thing is the real-time communication. So basically in the real time, the time is critical. And for that, there are actually several papers. One of them is called SPEED. This is the name of a scheme in which they have geographical routing. So geographical routing means as opposed to what we have in IP, which is address-based routing. In geographical routing, you just everybody knows their location, and then you send it to your neighbor. So you send your packets to the neighbors in the direction of the destination. So we want to go there, and so rather than trying to find the optimal path, we say, okay, well, one packet wants to go north. In the north, my neighbor is this. I will just send it to that one. And so that's the geographical part comes in, is that if we know the direction of the final destination, we can send roughly in that direction to the neighbors. The nodes send a delay feedback backwards as the packets are forwarded. And the nodes can also send a back pressure message if the delay is too high. So what that means is if some node gets the packet and the next hop delay is too high, then it could say, well, sorry, now don't send too many packets because now they're not going to make it in time. Right? So back pressure means don't send any more. So the nodes can send a do not send message, a do not send further message if the delay is too high for the further hops, and select the neighbor with the least delay. Now, since you know the delay from the different neighbors, if you want to go north, you select from all the neighbors that are in the north direction by looking at that delay. If no neighbor can meet the delay constraint, the packet is dropped. Now, every packet has a delay deadline, so you say, well, the deadline is 10 o'clock, it is 9:59, in 1 minute, sorry, can't make it, then you drop the packet. And when nobody is close to the destination, that is called a void. So void is simply a name is given that, sorry, it cannot make it, not because of time, but because of reachability. It's not reachable. The destination is in a void, means it is unreachable. So you want to avoid that, and you want to issue a back pressure with infinite delay. So what you do is you tell people that, look, you cannot reach this destination, period. So one way to do that is sending a back pressure message with infinite delay, and that way they will find some other path for it. So that's a speed. So what I've done is I've just taken a simple example. This is not the only scheme. There are many other ways of doing real-time communication. I've taken a sample one here. Okay? And in this one, this is what they decided, that they will do back pressure, they will have this and delays going backward, so you know the delay of your neighbors, delay to your neighbors, and then based upon that you do the selection of how to go. Okay? Any question about that? All right. If not, then we are at the end. So what we have done is we have talked about 3 standards, and then actually the 3 standards are not correctly listed. We have talked about 802.15.4, which is the phi layer. Then we talked about 6 low pan. Let me change that to 6 low pan. While the previous statement was correct, but we didn't talk about it, so I'm just going to remove it. 6 low pan. Are common protocols. And WirelessHART. Now you know what is WirelessHART, right? Anybody remembers what is first of all, anybody remembers what is 6 low pan? What is the problem? Forgot? What is 6 for? What is number 6 there for? IPv6, right? So now you know the problem. Okay, yeah, go ahead. What was your, David, what was you saying? Breaking the, so one of the problem was breaking big IPv6 packets into this tiny pan. Right, okay. And then the WirelessHART, what is that for? Yeah, remotely controlling devices, industrial devices. So that is your sense and perception. All right, then we talked about a number of research problems. Location discovery. For location discovery, the key is this triangulation thing. And we do the same thing in GPS as well. Then we talk about quality of sensor networks. And that is where we wanted to find path which was farthest away from any of the targets. So that is the quality of time synchronization. By time synchronization, we exchange timestamp and then estimate the one-way delay. Once we know that, we can do the timestamping. For the transport, we had this PSFQ, which is pump slowly and fetch quickly. And then for real-time communication, we had to use the deadline-based forwarding, where we basically find out the neighbor with the least delay. If that one doesn't meet the delay, then deadline is exceeded, and then we have to drop the packet. All right? Any question about any of the topics we talked about? None? Then I will. These are the Wikipedia articles all over again. The book, Murthy by Manoj, does have a chapter on research topics. So many of these research problems that we talked about are discussed in that book. And here's the homework. The homework is that you know your location from these 3 points. These are the 3 distances. What is the coordinate of x? It's a very simple geometric problem. We don't have to give it in graduate school, but that will just, doing that problem, you will figure out as to how the position is found out. That's all there is. Any question about the homework? You think you can do that? It's okay? That's it then.